Hello and good morning, grade 9 with you, Mr. Samir Awad. And today we are going to start our second part of distinguishing among atoms. And that is talking about the mass number and the atomic mass, how to calculate it. Atomic mass. How do you calculate the atomic mass of any element? The mass of even the largest atom is incredibly small. Since the 1920s, it has been possible to determine the tiny masses of atoms by using a mass spectrometer, and the mass of a fluorine atom was found to be 3.155 times 10 to the power negative 23 grams, and that's too small and impractical to use in life. So, such data about actual masses of individual atoms can provide useful information, but in general, these values are inconveniently small and impractical to work with it. So, instead, it is more useful to compare relative masses of atoms using a reference isotope as a standard, and that reference isotope was chosen as carbon 12. It means that the carbon atom and that's isotope 12. So this isotope of carbon has been assigned as a mass of exactly 12 atomic mass units. So an atomic mass unit, AMU, is defined as 1/12 of the mass of carbon 12 atom. So if I said a carbon 12 atom has 6 protons and 6 neutrons in the nucleus, and its mass is set as 12 AMU, atomic mass unit. So the 6 protons and the 6 neutrons accounts nearly all of this mass, and therefore the mass of a single proton or a single neutron is about 1/12 of the 12 AMU or about 1 AMU. So if I'm talking about the hydrogen atom, relative to the carbon 12, it will be the mass for the hydrogen 1 AMU because it has only one proton inside. On the other side, if I want to the helium, it will be 2. So it can carry 2 AMU, 2 protons are inside for it, and 2 neutrons, so 2 plus 2 will be 4 for the helium. So in nature, guys, the most elements occur as a mixture of 2 or more isotopes, and each isotope of these elements has a fixed mass and a natural percent of abundance or existence in this nature. So here we'll get, for example, hydrogen 1, 1, and hydrogen 1, 2, and hydrogen 1, 3. So hydrogen 1 and hydrogen 2 and hydrogen 3 will get different, natural abundance here. And the mass here is different too, according to AMU. And by the end, we'll get the average atomic mass for them to be representing the most abundant one. And on the other side, helium will be 2, 3, and 2, 4, helium 3 and helium 4. Helium 4 will get the most percent of abundance and its mass is 4. So when I get the average will be nearly to the mass of the most abundant one. Not likely we'll get another one like chlorine. You have to make some calculation in order to get its average mass or atomic mass. Chlorine here occurs in 2 isotopes or as 2 isotopes, chlorine 35 and chlorine 37, and the difference between them exactly the number of neutrons, 18 and 20. So if you calculate the arithmetic mean of these two masses, for example, you will get the average, so you will add both together and after that divide by 2. But that will give you another mass which is not represented to their actual representation inside our nature or the natural abundance of them. So we have to do some calculation according to the percent of each one. So chlorine 35 will get the abundance of 75%, and the other one, chlorine 37, will get the abundance of 24 or 25% around that. So if I get the difference between them, so each 4 of chlorine atoms exist in the nature will get 3 of them of chlorine 35 and 1 only will be of chlorine 37. So if I want to get the average, I will calculate all of their protons together, and I will calculate all of their neutrons together, and by the end I will add the protons to the neutrons to get the overall atomic mass and divide it by the number of these atoms, which is 4. So 68 will be the number of protons plus 74 the number of neutrons divided by 4. By the end I will get, according to their percent in life, I will get the most correct average mass for them, 35.5 AMU, and that's for chlorine. So the atomic mass of an element is the weighted average mass of atoms in the naturally occurring sample of this element. And the weighted average mass reflected both the mass and relative abundance in the nature for the isotopes. Yeah, let's get more to know about the relative abundance. If we get here copper to be getting the mass of 63.546 or 546 AMU, atomic mass unit, which of the copper 2 isotopes, copper 63 or copper 64, will be the most abundant? So relative to that, guys, it's 63. So it's near the 63 one. Exactly, it will get the most abundance for the copper 63 to be the most abundant isotope at the more percent in the nature than the copper 65. As you can see here, guys, during that you can start to weigh the mass or the average mass for them in the nature. So here you will get that the copper 63 is going to be more by determining the abundance of both. So I will know that the copper 63 will get more abundant there. Exactly, that's a relative abundance for it. To do this, you must know 3 things. Number 1, the stable isotopes of the element, copper 63 and 65, the mass of each isotope, that's number 2, and the natural percent of abundance I have to know too. So that's what I have to do. To calculate the atomic mass of an element, multiply the mass of each isotope times the natural abundance of it expressed as decimals, not as percent. And then add the products. For example, here, guys, we have here the abundance of the carbon 12 is about 98.89%. And on the other side, the carbon 13 will be 1.11. So if I want to calculate the average mass for them, so well, get the mass of carbon 13, which is 13 times the percent of it in form of decimals, so it will be 0.0111. So I will make that 13 times 0.0111. On the other side, 12 times 98.89 divided by 100 because I want it in decimals. So it will be 12 times 0.9889. So the overall here will be the average mass for the carbon 12 and the average mass for the carbon 13 according to their abundance. And the overall of them will be give me the average mass for the carbon at all, or the average atomic mass of carbon, which is 12.011 AMU atomic mass unit. So calculating the atomic mass unit here is getting you to start to know more about that. Element X has 2 naturally occurring isotopes. The isotope which with the mass of 10.127 AMU, so X will be around 10 mass, has a relative abundance of 19.91%, and the other isotope, which is 11, is getting to get the percent of 80.09. Yeah, calculate the atomic mass of this one. I knew that one, it will be sodium, but for existing, we will know more about that, guys, in order to get the atomic mass and know by the end which of them will be the atomic mass for what. So here I have to make the mass of each isotope times the relative abundance to get the average mass of this isotope, and by the end I will add them together. So the first one is 10.012 AMU times the percent of it in decimals, it will be 0.1991. And on the other side, I will get for X11, the mass will be 11.009 AMU times the relative abundance of it in decimals, it will be 0.8009. So by the end, I will get the first one and the second one, and we'll add them together by the end. So the average mass for it will be 10.810. So if we get that, guys, that will be relative to the mass of what? Getting to be 10. It's likely to be for the element with mass 10. Does the result make sense? Yeah, the calculated value here is closer to be more going to the direction of the abundant isotope more than the other one. Why the atomic mass of an element usually not a whole number? That's because it's getting to be like getting two things, the mass and the abundance of it occurring, and this percent will be exactly a percent, wouldn't be a whole number. So that's what we get, guys. The elements are different because of their atomic numbers and number of protons, and the isotopes of the same element have the same chemical properties, and also they are different only in the number of neutrons but have the same number of protons. And to calculate the atomic mass of any element, you have to multiply the mass of it times the percent of it natural abundance, yeah, in form of decimals. And after that, add the two isotopes or more than two isotopes. Never forget that the number of neutrons is equal to the mass number minus the atomic number. And never forget about the atomic mass number and isotopes definitions, guys. Atomic mass unit and atomic mass. And by the end, guys, know more about the atom structure, electrons, protons, and neutrons. See you later, grade 9. I was with you, Mr. Samir Awad. Stay safe at home, and good luck, guys.